Hello guys, can you see my screen before I start?
Yes.
Okay, so a small recap of our previous class. So we learned about machine learning. We compared how a machine learns to the rule-based system, like the normal programming. We said that for normal programming, you have to define the rules, like give it a case. If this condition is met, proceed. If it's not met, go to this point, and so on. But now for the machine learning algorithm, we just give it data, then it learns from the data. Then when we give it a new information, it's able to give us an output because it has already learned. Maybe it has already learned some patterns and so on. We also learned several ways in which machines are trained. For example, we have the supervised learning where we said like we are giving it a labeled data. We are teaching it with the answers. It's like giving it uh, questions with answers. Then I will give it an exam, so it's able to answer because it's already familiar with the data. Then we said we have the unsupervised learning where we just give it data. We have no expectations because it's going to learn from the data. Then we have the reinforcement learning where it's a rule award system. It's learning from the environment. So if it takes this move, then the environment responds negatively, it's going to know that's not the right move. So it's going to take a different move. Then we have the semi-supervised learning where we said we train it with a small, it's a sub-supervised learning. We train it with a small amount of labeled data, then large bits of unlabeled data. Then we said there's another one that's called self-supervised learning. And also because it's already an evolving field and we have like a lot of research on AI that's going on right now. So of course there are other things that are coming up. So maybe in future you can meet others. Yeah. So we looked into those algorithms. We said when we are training a machine learning model, we are trying to reduce the error. So because it's learning from the data. So the first time it is learning, it won't capture everything. So when you're trying to make it predict, it won't predict as we want it. But now we want to reduce the error. We want it to predict as close as possible. We want it to give us the correct answer. So the variation between the correct answer and what machine learning has on what the model, I use the model name, what the model name has what the model has predicted, that difference between the right one and the model output is called the error. So as an AI and ML engineer, it's to make sure that that error is as small as possible. Because if the error is small, then the machine has learned the model has learned well from the data. But also we talked about several aspects, this overfitting, where the model can learn so much from the training data that it is like cramming the data. So when you give it new information that it has never seen, it's not able to maybe make a prediction because it's not the data that you've used for training. So it's not able to give a good output for new data. So we said we are creating a balance between training it well, but making sure it's not overfitting, make sure it's not underfitting, making sure it's robust. It's scalable, it can grow, it can take in new information, be able to draw patterns from the new information without cramming the information. I'll use the cramming term. Yeah, and also we said, how do you even measure that error? We said the error, the difference between what the model has predicted and what the actual output is the error. How do we measure the error? So we said we have for regression models, we are measuring through several methods. For example, mean squared error, mean absolute error, root mean squared error, and R2 score error measurements. And then for regression, we said we are going to measure through, I gave like a confusion matrix, like we have the accuracy, we have the precision, we have the recall, depending on what you want to achieve. Yeah. So that's just a recap. So we are picking from there for today's class. So we are going to learn important machine learning concepts, and then we are going to learn common machine learning algorithm by the end of today's class. Okay, so I think I need to explain much more before I go in deep into the notes. So when you talk about algorithm, I know you guys, it's not the first time you're hearing about an algorithm, but basically, okay, the normal meaning of an algorithm is just a set of rules. It's like, let's say even a recipe. A recipe is an algorithm because you're telling, from the recipe we can say this is the first step. Cut your onions, light your cooker or something, do this. It's like a set of rules. Like at the end of the day, that will the rules are going to achieve something. So basically, an algorithm is a set of rules from its definition. But now we have the computer algorithms. For example, functions, classes. A function is like an algorithm. You can write a very long function. It's like you're telling your program, do this. This is the first step. When we give you a number, take it, multiply by 2. After you multiply by 2, do this and do this. So I expect you to return this as the output. That's like I'm using the syntax of a Python function. Still, that's an algorithm. Now we have now the machine learning algorithm. So machine learning algorithm, it's the same thing. It's a set of rules that have been prepared in a way that we can give it computer. But now for the machine learning algorithm, they learn from the data. So they learn using different methods, and then the output, depending on the various methods. But now you can ask yourself, where do these algorithms come from? For starters, starting comparing with the normal computer programming algorithms, we have the computer, then we have the programming languages. So we are able to create system by giving a computer instructions. Basically, that's it. But now, because now our machine learning algorithms, they learn from the data. If you're asking ourselves where they come from various domains. For example, statistics. We know that the statistics field is used to, it's like a mathematics field where we can do data modeling. Researchers, let's say researchers, statisticians, they're able to model data relationships. For example, probabilities, regression. Regression already exists in the statistics world, you know. We have the linear algebra. We have linear algebra. It's a mathematical topic, you know. We have calculus, so etc. So researchers come up with algorithms based on those methods, maybe statistics, linear algebra, and calculus. And now we use computer science to turn that math into a step-by-step procedure that computers can follow. That is now the algorithm, connecting with the rule, step-by-step procedure, the algorithm. And now the computer aspect is able to help us optimize, create that algorithm, and in a way that a computer can understand and a computer can use it. So by the end of the class, we are going to look into various machine learning algorithms, see how they work, see how they function, and probably see when to use them. I think that's just the overview of today's class. Secondly, we need to know now for this slide now the different training methods. How does a computer learn from data? I think that's a big question. How does it even actually learn from the data? So I'm giving it data, then I'm expecting it to learn. So how does it actually learn? So there's the algorithm aspect. The algorithm aspect is different ways in which a computer learns. But now, how does it learn? So for starters, a computer, it's going to now that's where the gradient descent comes in. I'm trying not to read the slides. I'm trying to explain it before I read the slides. So, for example, a computer will start from a random point of learning. They've just given me data. So, let's say I'm the computer. So, I'm starting from a random place, learning from this. Then, as I learn, I'm going to output and see if I'm actually learning well. If I'm not learning well, I'm going to improve. So it's like an iteration process where a computer, it just starts randomly, honestly, how it's designed, starts randomly, then it learns as it improves, and so on and so forth. So we are starting with machine learning training method. We have a method that's called gradient descent. We can call it an optimization. I don't even know why I've called it training method. I think these are contradictory. Optimization method. Yeah, it's optimizing how a computer learns from data. Okay, so we are training the data using those methods that we've said use maybe supervised and supervised. And now we are optimizing, which means we are adjusting the parameters. We are adjusting how it learns. Then at the end of the day, we are trying to reduce the error. So that's like the overview. So we have a method that's called gradient descent. It uses a negative gradient direction of the current position of the search direction. How do I explain this? I'm starting from top. I think this one is a visual illustration of gradient descent. Let me just pen a new slide. I want to draw something. I don't know if I can draw randomly in my PowerPoint. Okay, PowerPoint's guru. Can I draw randomly? Can I just pick like a pen then and start drawing? Okay, I don't see a way that I can do it. Apologies, guys. So it's like it's starting randomly from the high point there, the point where my cursor is at. Then it's going to, at this point, it has not learned anything from the data, or maybe it's just learned like a small amount of information from the data that you've given it. Then it's going to adjust. So it's a random point. So pick that point, then not yet. Practice more, not yet. Practice more, not yet. Practice more until it's like it's leveling up. So this lower point, it's like it's leveling up. The curve is leveling up. So at this point, it's like it has already like learned like a lot of things from the data. It is able to draw several patterns from the data. And now it's like it has optimized the training. So let's say gradient descent is a way of optimizing the process of a machine learning or machine learning process. So we have various ways, various methods, or various gradient descent method. I think I had some small notes here. So gradient descent itself shows a decreasing descent in a very small range close to the target point, but the gradient may fluctuate in specific range of a target point. But how it starts, it's just random. It starts from a random point, then it optimizes until it reaches a point where it has learned. This is the formula for gradient descent. I told you it's important to know how they function, but don't cram the formula per se. What's important is to know how it works. Yeah, so this factor is called a learning rate. So when you're training machine, an algorithm or a model, let me call it a model, there's a learning rate. It's like you're saying it's a rate at which the machine, how it's the rate at which the model learns. Then these are the data points, etc. I don't know if we are together here. I don't want anybody to be left behind. So any question on this slide or on gradient descent? Or have I clearly explained what it is about? So in summary, gradient descent, it's an optimization method that helps an algorithm to learn by gradually reducing the error, as I've said. So we start randomly, it has not learned, then it learns more. So the more the process is going, the more our model is learning from the data, the more accurate our output. So the lesser the error. So that's like a summary of it. So any question or any comment? Okay. So we have three main gradient descent types of gradient descent. The first one is the batch gradient descent. It's where it's like it uses all the samples from the data set. So it's going to use all the samples from the data set to update the I need a visual for this. Let me just open, what is it called? Paint. Okay, so allow me to introduce like let's say a neural network. Um, Basically, a structure of a neural network. We have the input layer, then we have another layer that's called hidden layers. These are like the layers where like decisions are made. As the decision proceed, the more our model is learning from the data. You can have as many as possible, but the more the hidden layer, the more complex the model becomes. So this is for deep learning. I also want you to know that there is machine learning and deep learning, but I think this one is a bit good example. So we have our input. We want it to learn from the data. So we have our input here. This input go to this layer. So each input passes through each attribute of the hidden layer. This one is also going to go the same. Then the pattern continues. Okay, I want to draw everything until the output layer. So maybe in the output, we are trying to classify, um, let's say that's the sentiment analysis thing. Is this comment negative or positive? So it's going to output two classes. These comments belong to negative. These comments belong to the positive, etc. So when we are learning, when we are giving our model data, it doesn't know anything about the data. So it's trying to guess. It's trying to guess. Even when you're learning something for the first time, you don't know it. Then when you repeat, you start understanding. Then you repeat again. Then you repeat again. Then now it becomes so obvious to you. You know, it's just the same way here. So when you talk about the weight, it's like those simple things that a model uses to determine which category this belongs to. So for example, it's going to make some weights. This comment, it falls more, let's say it's heavier on the negative comment than the positive comment. So like this, the weight factor is what the model uses to determine which maybe category our output falls at. So our gradient descent here is used to optimize the learning. It's used to tell the model, no, you have not yet learned enough. Continue learning. No, this is better. This is better. The error is reducing until now we reach a point where the error is completely reduced. We can't get a zero error per se, but we are trying to aim for the minimum error. So for the batch gradient descent method, it uses all the data points, all each and every data point. So it's like you're trying to use all the data points to train a model with. So it's not usually the most effective, because if you have large data, the learning tends to be slow. For stochastic gradient descent, it chooses random data points or random data samples. This is faster, but maybe if it's just random, if you're picking randomly, also it has its own disadvantage, because the machine, it's faster, but it's not optimal. It's not going to learn very well from the data because it's just random points. But now this mini batch, it's like a combination of the batch and the stochastic gradient descent. So it groups training data into several samples, then it picks randomly. So you see, it's not a single data point. It's like when you pick it randomly, it already contains several samples or several data points. So it's like a combination of the batch gradient descent and the stochastic gradient descent. So this one is usually the best method. Okay. So this is just a more explanation on how what I've told you. Batch gradient descent uses all training samples. It's like trying to learn everything from the data, but and then adjusting it, then now reducing the error. It's slow. And then stochastic, it's randomly picking randomly. So it's fast, but you can if you're picking randomly, you can pick the same data point twice. So it's not optimal. Now this method is the most optimal. Yeah, so gradient descent basically it's an optimization method to make sure that our algorithm is actually learning from the data so that we can create the model. That's the summary of it. So any question or any comment?
I have a question.
Yeah.
In the mini batch gradient descent,
Mm-hmm.
as much as it's picking samples from the data
Mm-hmm.
and then choosing it randomly,
Mm-hmm.
can it also not maybe choose certain samples of data, and when training, then the model might not have that specific data?
Okay, it's like it's creating a balance. You see, if it has if we are combining several samples into what do I call? We are talking about the mini batch, right?
Yes.
Yeah. So let's say I'm putting 10. I'm grouping several samples, let's say 10 samples per group. Then I can have as many groups as possible from my data. So when I'm picking it randomly, yes, maybe I can pick twice, but then chances are it's going to learn better than these two other methods. Like I understand your concern, but it's like the better method. But and also how they are designed, at the end of the day, it's going to, at the end of the machine learning, because we are trying to reduce the error. So if it has not learned well from the data, still the error is going to be high. So how do we know that an algorithm has learned from the data? When the error is reducing, when now the output of our model versus now the, let's say the actual output, they are so close. So in as much as there's a probability that it can learn randomly and maybe fail to learn from the data, we're also monitoring, how is the error? You get the point?
Yes, yes, I do.
Yeah, so that's why most of the times it's going to learn well. At the end of the day, it's going to, you know, learn from all the data points. Okay, so we have other we have in when you are training a model, you are going to meet parameters and hyperparameters. These are like terms. So parameters are what our algorithm learns from the data. So it speaks for itself. So you remember when I told you our clustering algorithm, we don't even now for those clustering algorithm, we don't even know what they are going to find from the data, which means the algorithm itself it's able to pick some parameters from the data for it to come and group this data belongs to the same group, this other group belongs to the same group, this is the pattern from the data. There are some parameters that is going to pick on its own. So every algorithm has its own ability of picking parameters from data. So we're not the one who is setting this. It's according to the data, the algorithm will pick parameters. But now the hyperparameters are the ones that we are in control of. As an AI and ML engineer, you are in control of hyperparameters. You can control the speed at which your model is going to learn. You can control how many times the model is going to learn. You can say repeat 20 times, learn again until you understand, you know. So these are called hyperparameters. So parameters are automatically learned by the models from this part. So these are just a picture illustration. I thought a visual would show better. So we are training a model. So parameters are picked from the data. But now our hyperparameters are the one like which are firing the model. They have said there's a point that you can control the rate at which the model is learning. You can control how many times it's learning. You can control how it's going to learn, etc. So we have several hyperparameters, and different algorithms have their own hyperparameters. Yeah. So don't worry about the parameters because that's for the model. But now the hyperparameter part is what makes you a great AI and ML engineer, because if you're able to choose or to pick your hyperparameters well, then your model will not overfit, will not underfit. It will be robust, which means you are capable of coming out with a good model from the threshold. You remember we said we defined what a good model is. So we have several example of hyperparameters. So hyperparameters are commonly used for model parameter estimation as specified by the user. I think this part should be by the trainer. They are set historically. You're the one who is determined according to your data, according to what you want to achieve with your model. You know, there's no like given rule according to how the model is learning. You're going to determine based on the output. So that's why machine learning or even deep learning, when you are training a model is usually considered expensive and resource intensive because it involves tuning parameters, hyperparameters. You tune this, then you realize no, this is not the best one. You retrain again, you tune this, you tune this. It's a whole process. Now that's where now the work comes in. In as much as the algorithm is doing the learning, you are still in control. It's not like the algorithm will do the learning, but now you can control it. And that's where the work comes in. That's how you create a good or a bad model. So we have several examples. Don't worry about these terms. You're going to learn about the is this region lasso. So we have this parameter. Is it a lambda? It's called a lambda parameter for region lasso. We have the learning rate. This is for neural network. You can adjust the learning rate. You can adjust the number of iterations. It means the number of how many times it's going to learn. So they are called epochs. So when you're training your deep learning model, there's a part where you can set your epochs. You say 20, 30, 5, 1, depending on how many times you want it to learn. We have the batch size. So the good thing about training a model, once you have trained it, you have trained it. You get me? So the training part is the hard part. But once it has learned from the data. So that's like a good part. So you can control the batch size. It's like how do you want the data to be learned? So for neural networks, they use a lot of data, like lots. Like I'm talking of terabytes and terabytes of data. So you can pick batches, like you can set the batch size, how you want the data to be learned. We have another factor that's called an activation function. You're the one who is going to set. We are going to learn about the activation function in the near classes. The number of neurons in a neural network. You can even pick, I think I've drawn an input layer, then hidden layers. For some model, you can even pick how many hidden layers you want in a model, you know, and so on. So the fact that you're the one determining those factors, it's hyperparameters. So we have a machine learning algorithm that's called support vector machine. Don't worry about it. We are going to learn in the next slides. It has the C parameter and this one. This is called it's not beta. That's this one. I've forgotten its name. Yeah. We have another algorithm that's called K nearest neighbors. You're able to set the number of Ks. We have another algorithm that's called a random forest. You can set the number of trees in a random forest. So these are things that, this is just an example. So each algorithm has its own hyperparameters, in short. So which means for each algorithm, there are some things that you can control, how the model learns. I think the next slide is also explaining the same things. Yeah. Yeah, it's explaining the same thing, but now in a process. For example, we start by dividing our data into training, validation, and test set, but I'll be using training and test set in our classes. Then you optimize the model using the training set based on the model performance metrics. So we talked about optimization, gradient descent. So the model starts to learn, you train it, you test if it's learning well. So we talked about the evaluation metrics. Then you search for hyperparameters using validation set. The validation set based on model performance and metrics. So based on how the model is performing, you're the one who is going to say, let me increase the number of Ks in my K nearest neighbors algorithm. So if you feel it's not learning well, you're in control of the hyperparameters. Then you perform step 2 and 3 iteratively until you feel like, yeah, this is what I want. The performance is well. This is what I was aiming for. The accuracy is 99%. The precision is 90%, depending on what you are looking for. And now you can, from there, now you can see what, depending if you're deploying, if you're giving it new data to see how it's performing in real world and so on. So we have various ways in which you can set your hyperparameters. I know from this previous step I mentioned this hysterically. It's like from your own, depending on how you feel about your training, you know. But now we have other methods that are defined to help us set our hyperparameters well. So we have the first method, which is grid search. Grid search is whereby, let's say, I'm training a neural network, because I'll use that because for this we have given different types of hyperparameters. So I can put a combination. I can say let the learning rate be 0. Usually learning rate is in 0 point something, 0.01, 0.05. So I can see learning rate will be 0.05. The number of iteration will be epochs will be 20, batches will be 12, activation function, I use this and this. So I put them in like a list. So the model is going to, no, you see, it's like you've set all your hyperparameter in one list where the model is going to pick from, you know, it's going to learn as per your list. So that's called grid search. It's like a way of making hyperparameter tuning easy. We have a random search. It's random search is where you give it several options. You're giving it several lists. Several lists. Then it's going to pick from the best combination, you know. Yeah. Then we have the human intelligence. You're the one training. You're the human factor. You're able to tell, I have put the learning rate to this and the accuracy has increased, which means if I increase the learning rate a little bit, maybe I can achieve what I want, etc. Then we have another method called Bayesian search. This is not the most common one. These two are the most common one: the grid search and the random search. So, any question? Any comment, or are we together? I think that should be. Are we together up to there?
Yes.
Okay. So this is just more explanation for these methods. So I'll just call it hyperparameter tuning method. So we have the grid search. So it usually performs an exhaustive search of all possible hyperparameter combination from hyperparameter value grid. So I think take the value grid as now the list that you've given it. So what does it do? It's going to check, if I combine this and this, how is the performance? It's like it's trying all the possible methods. So remember, we have given it a list, but it's really a long list. I know I've just talked about a list. Like it's like a simple, not a simple, it's a complicated, a long list depending on what you want. So it's like you're telling it, check this and check this and check this and see how will be the performance. Check this and check this. So it's going to perform all combinations of the given range until it chooses the best combination of hyperparameters. So you don't have to do the manual work. You're just going to set different combinations. Then the research is going to do the work for you. Then at the end of the day, it's going to tell you this is the best combination. When you put the learning rate to this, then the batch size to this, then the epochs to be this and this. This is the best combination that we have for now. So from the best combination, if you're not satisfied, you can choose still give it another list based on the best combination. Then it's going to do an exhaustive search until it gives you the another best combination. So when it comes to model training, you're the one who is going to determine when to stop training if it has achieved your level of accuracy or the level of accuracy that you expected. Things for the random search now, it's a random search. So it's easier than the grid search, but sometimes depending on the amount of data that you want to you are training or okay, considering the circumstances, you're the one to choose which one you're using. So I think the biggest part about being an AI engineer, it's being able to identify, is this going to work for my data? You have to be aware of your data, you have to be aware of your goal, you have to be aware of what do I want to achieve. So which algorithm should I use? Which method should I use? Which are the hyperparameter? How do I want to test my error? So as you can see, these are several options. So I've seen some people in different hackathons, they usually train different models using different algorithms, using different methods. Then at the end of the day, you are going to pick the best model that you've come up with, depending on your data. So these are some methods that people choose out there. So as the human factor in training the method, training the model, you're the one who is going to determine which one is which. Is this the best one? Is this the good given my circumstances, and so on. So the random search, from the name random search, it will pick as a random sample of combination of hyperparameters. Then from there it will work towards becoming better to find the most appropriate combination, you know. Yeah, it is same. So any question on that?
I have a question.
Yes, yes.
In random search,
Mm-hmm,
you said that it will pick a combination of the hyperparameters
mm-hmm,
and then it will work on becoming better. Does that mean that the combination of the hyperparameters picked are the ones that will be made better, or will it pick that fails, it picks again, that fails, it picks again,
mm-hmm.
like that?
So um so one thing for starters, we are the one setting the hyperparameters. It's in our power. So like random search is like a method of picking the best hyperparameters. So when it's picking from the best, let's say for example, I think I need my task. It's not working. Let me just open a new slide. Let's say we have a learning rate. I'm just going to say learning rate is equals to 0.001. Then to say, let's say epoch is equals to 12 or 10. This epoch is the number of training that's going to happen. How many times do you want to repeat the training? Then they say the batch size is equals to 16 etc. So for random search, you're going to give it different combinations. So let's say it has picked this one and realize this is the best combination. It's going to work from there. So it's going to adjust. Now if the learning rate combination, if this plus this is equals the accuracy of 87%, and then maybe there was another combination of I'm trying to see the best way to explain this. But just let me see. 55. Let me say 8, then maybe the average accuracy will be, let's say 60%. Okay, let me think if this is the best way to explain it. Okay, so the point is, instead of using a fixed set of value, you're defining a range or a distribution of values from which samples can be picked. So it will pick a sample combination, then it will realize this combination is better than this. So it's not going to reduce the learning rate. As you can see, for example, according to it, I don't know the logic behind it. I'm just like explaining. From this combination, we can see that maybe, okay, I think I should do something closer to 9. Let me do 12. That would be easy to understand. But now this one has a higher accuracy. So I'm just imagining, according to the random search, is going to say now, I won't change the learning rate. I won't increase the learning rate because this is a higher learning rate, but the accuracy is low. So it won't go here. It won't pick this parameter again, and it won't go near this parameter again. So it's going to play with these other combinations. That's a random explanation, assuming. But what it does, okay, it's picking a random combination, but it's not. It won't repeat the mistakes again. But now for grid search, it's exhaustive. It's going to check this combination. When I pick 0.01, then combine it with 10 and combine it with 16, what am I getting? When I pick this, and it's different from exhaustive. So for random search, it's able to learn that going this way won't benefit my accuracy. So I think that's a better explanation. I don't know. Have I answered your question?
Yes, but does that mean that the accuracy is calculated before it is tuned into the model?
Not really. So you see, we are still training our model in this situation. And also, as the person training, you can set these things manually. You can, for starters, you can say, let me start with this combination, then see the accuracy. Then you set another combination, then you check the accuracy, you check another combination, then you check the accuracy. We are still training our model. But now, instead of doing that manually, you're going to utilize this either grid search or random search. So you're going to give it different hyperparameters. You're the one choosing the hyperparameters. So you're going to give it a lot of, let's say, several learning rates, several number of epochs, several batch sizes. Then you're trying to tell it, test for me. So instead of me testing, you test for me until you find the best combination. Then now give me the best combination. Then now we can, from there we can evaluate. So it's like we are still training. The accuracy is not set before we train the model, but now, as I said, the training, it involves us checking if how is the error, you know. Then I also talked about the optimization part. Is the error reduced completely, you know? If the error is not reduced, if you're training your model, then you're getting 60%, because we said hyperparameter is in your power. You can try to change some hyperparameter. But now, instead of every time you're training the model, you're evaluating, you realize no, it's has increased from 60 to 65%. This is still not good. You go and again do a combination of hyperparameters, because we are in control of hyperparameters. Instead of doing that, you're able to give various ranges of hyperparameters. Then let's think of it, grid search is like an algorithm for choosing hyperparameter combination. So for grid search, it will do it exhaustively. It's going to try each and every combination. But now for random search, it's going to learn from the process. Are we together?
Yes,
Yeah. So have I answered your question?
yes.
Okay. Any other question?
I have a question.
Yes.
So if I'm understanding you right,
Okay.
in random search, the
Mm-hmm.
hyperparameters, like the combinations, are
Mm-hmm.
like it's the machine that predetermines it or determines it based on like the accuracy. And
Mm-hmm.
in grid search, it's
Mm-hmm.
like we have predefined combinations that it's testing out. And then
Mm,
it will choose the best combination based on the accuracy.
okay. Um, okay, I want you to think of it this way. You're the one choosing the hyperparameters. But now, okay, I think I think my example is bad. Let me use another example for grid search. So you guys remember dictionaries? This is now where these data types come handy. So let's say I say learning rate. It's like a mini code, learning rate. Okay. Then I give it a list. 0.1, 0.5, 0.8, 0.0, okay, 0.1, 0.005, 0.05. I think that list is enough. Then I come for this is just an example, batch size. So you, as the one who training the model, you're the one setting this. Okay. So batch size. I can say I start with 6. I don't even think you can start with 6. 8, 12, 16, 32, maybe 64. Then you come and say epochs. Give it a list. Let's start with 5, 10, 15, 20, and 25. So you, the one training the model, you've given it these different combinations. So it's like you're trying to tell it, test these combinations and give me the best. You don't want to do it for yourself. Now grid search is going to do it exhaustively. Take this, combine with this, combine with this. Like it's going to do all the combinations that are here. So if you're a mathematician, I think it's this times this times this. I think, yeah. So the grid search is going to do every combination, all of it. Now, after doing all the combination, it's going to say, this combination the best. Finally, after I've done all the combinations, finally, maybe this 0.01, maybe 12, maybe 15. This was the best. But now it is drawing this conclusion after it has done all those combinations. But now for random search, it's okay. You might give it the same combinations, but it's like it's going to learn as it goes. So let's say it can do some combination, then realize this combination is not adding the accuracy. It won't go ahead with that type of combination. I don't know if I'm explaining the point clearly to you. So you, as the trainer, you're the one who is setting these parameters. But now instead of doing the combinations for yourself, this grid search and random search are the ones that are helping you test the various combinations to come up with the best. But now they do it differently. Have I answered your question?
Yes.
Uh-huh. So I have answered your question clearly. So like you have said yes. So I don't know if are you satisfied with the answer?
Yes, but my question is
Mm-hmm.
now on grid search.
Mm-hmm.
Now, like I understand, like the hyperparameters are defined by the trainer,
Yeah.
but could you clarify on how each method now chooses those
Okay.
or goes about choosing the best combination?
Okay. So for the grid search, as we said, it's exhaustive, which means it's going to test this the first learning rate against all batch sizes, all epochs. So it's because already itself is like an algorithm. It's recording the results somewhere in a small memory. Then go to this one. Test for all the batch sizes for all epochs. Then go to this one. Test for all the batch sizes, all the epochs. So at the end of the day, it will have done all the various combinations. It will have tested this learning rate with this, like everything, every I don't know if when I say every combination, if you're understanding that point, it's like testing everything. Then now, after testing everything, it is coming up with now the best combination that it has found. Are we clear on the grid search part?
Yes.
So for now, for the random search, how is it going to do? After okay, let me just draw the example. We are still using this. So for the random search, let's say for 0.1 and 12, okay, and 8 and 5, it has gotten like 40% accuracy. Then for 0.1 and 12, and 15, sorry, and 10, and 10, or I should retain the 5 first, because the first, it has gotten 50% accuracy. So you see, it's 0.1 versus this, and the 5, it's gotten 50% accuracy. It won't repeat the 8 again, because it has realized by increasing the batch size, already the accuracy is increasing. So instead of exhaustively trying all the combination, it's like it's already learning, realizing when I increase the batch size, I'm already improving my accuracy. So it can go now 0.1 by 12 by 10. I don't know, maybe 51%. So have you understood that concept?
Yeah.
Yeah. So for the grid search, even if it gets it sees an improvement, it's still going to do it exhaustively. But now for the random search, it's going to realize batch size, lower batch size, it's not improving. So I won't repeat that 8. So it's going to try other methods. So it's like it's already learning from those combinations until it comes up with the best combination possible. So any question or any concern or any explanation that you might need further? But also to explain the random search very well, I think I've gotten different POV. So you can just tell it, instead of now defining, you can just tell it, let me copy this one. Mm, 0.1. Then we see these are just a different method of setting the random search. 64, then maybe epochs 25. So instead of giving it a list, so sometime you might just give it this. So it's going to check the range. So from learning rate from 0 to 0.1, there's a lot of learning rates that you can come up with. The same for batch sizes from 0 to 64. There's a lot of batch sizes you can come up with. For epochs, the same from range 0 to 25. So it can still do the same. It can test different combinations randomly until it comes to the best combination, while still like learning from the combinations. So that's where the range comes in. So for some time, it becomes easier to deal with than grid search. But also grid search is good when you're already anticipating, you already know like this value might range between here and here. So the more you train models, the more you start seeing a pattern, or the more it's like, for me, when I train a model, then I get a small accuracy. I just know increase the learning rate, or decrease the learning rate. So I know when I decrease the learning rate, I know it's going to improve, but I don't know by how. So I can just let's increase with this. I give it like 3 learning rates, then I see which is the best. So grid search is good when you can already give some input. Then random search is good when you just don't care, come up with the best and give me my model. Yeah, I don't know, that's another illustration, but that's how they function. So any question, or so far what we've learned so far, any question? Okay, so just to add on this here, so sometimes you can find yourself just setting the number of random combinations. So it's like you're telling the model, just do random combinations, just do 50 random combinations, then come up with the best combination out of the 50. So that's still another way to view it. Okay. So are we together before I proceed?
Yes.
Okay, so we have another aspect when you are training that's called cross validation. So cross validation is a statistical analysis method used to check the performance of classifiers. It splits the original data into training set and validation set. So I think you remember when I said I'll use training and test, but then now we said you can split into three: training set, validation test, now the test set. So the former is used to train the classifier, whereas the latter, that is the validation set, is used to evaluate by testing the train model. So how does it work? You set the number of Ks. Let's use the K-fold cross-validation. K-fold, it divides the original data into K sizes. So each unique group is treated as a validation set. I think I need to draw this one. I don't know where I can't. Okay. Allow me to erase this. So I have my training data here. Let's say I divide it into 5 sections. So these are equal. So let's say, let me just even use a normal data set. Let's say I have a data that has 100 rows. So I'm going to divide it into 2020. Of course, you are not going to train a model with 100 rows. That's like small data, but that's just an example. So it's going to pick this as training. So for the first round, this will be the training. What's happening? For the first round, these 4 up to there, there'll be the training. Now this will be the test. Then after training and testing, it throws this into the group. So it's going to pick these 3 plus these 4. Now this will be the test for the second round. For the third round, this will be training, this will be test. For the fourth round, this will be training, all this will be test. So at the end of the day, we will have trained and tested with each data sample. So of course, this method, this cross-validation method, it has its own risks like data leaking. Already it's like you're telling the model, it has already trained with this batch, then you're testing with it. But we have like, when you're using it, we have several methods of making sure that the model does not remember those samples. So it's like at the end of the day, you will train with each sample and you will use each sample to test. I don't know if that is making sense. So let me see if the image that I've used for example makes sense. Okay, now this is the we talked about training and test set, but now cross validation. Now leave the test set alone. Now in this situation, now the test set now will be used as the new data that we are testing the model with. But now the validation test is the one that we are using for trains test. So the number of folds, when you say I want 5, my K is 5, it's going to divide the data into 5 sections. Then it's going to use 4 for training, test with 1. Do the same until it has done it for all the samples. If you set your K to 10, it's going to do the same. So this is also like another method of making sure, or just another method of checking the performance of, or maybe checking your training versus the performance of your model, especially classifiers. I don't know why it has specified classifiers, but yeah. So any question? Are we together so far?
Yes.
Okay. So now we are getting into now the common machine. So the above was just like several things that you're going to encounter when you're training your model. So yeah, you might need to set an optimizer, that is now the grid search. You will find yourself setting hyperparameters. You will find yourself maybe using the grid search or the random search depending on the situation. You might even find yourself using those the cross-fold validation. It's not all the time, but depending on the situation, it's relative. Okay, now we are getting into now the machine learning algorithms. So we have various machine learning algorithms that perform various tasks and use various methods to perform those tasks. So when I talk about tasks, you remember when we were starting this slide, we said we have the regression task, where mostly we are using it for prediction because the output is like a continuous, it's like a number, continuous value. Then we have the classification task. You want to classify situations. Then we said classification is not, it's not two classes only, you can classify as many classes as you want to. Then we have the uh, clustering task, depending. Now this algorithm, some are for regression, others for classification, others for clustering, depending on the tasks, and they perform it differently. So yeah, so these are like a tree summary of all the algorithms that exist so far. I know some might have come up by now, I don't know, but these are the ones that are used right now. So we have machine learning, we have supervised learning, and we have unsupervised learning. All right. So for classification task, we have logistic regression. This one is called support vector machine. Don't worry, we are going to do one by one. We have to understand how each works so that when you're training your model, you're going to choose maybe the best algorithm given the circumstance. We have the neural networks, decision tree algorithm, random forest, gradient boosted decision tree. So you can see this is like a part of decision tree. We have the KNN, it's called the K nearest neighbors. And then we have the naive bias uh, classifier algorithm. So for regression, we have linear regression, we have support vector classifier. We can have neural network for, sorry, support vector regressor, and we usually have another support vector classifier. Then we have neural network for regression also. We have decision tree for regression. So as you can see, some algorithms can do both, can do classification and regression. Some are just for classification, others are just for regression. We have the decision tree, random forest, gradient boosted decision tree, and KNN. For unsupervised learning, we have the clustering algorithms. We have k-means clustering, we have hierarchical clustering, we have density-based clustering, we have others, for example, principal component analysis, etc. So the most common one for clustering is the k-means clustering, the hierarchical, the density, and now the principal component analysis, etc. So we are going to start with the most basic one, linear regression. It uses regression analysis. What is regression mathematically? I think I'll draw this question to you. What is regression? Like the normal one. Trust me, you've met regression over and over. When you are plotting the y is equals to m, is it usually area? No, the formula of a line, a straight line in a two plane. It's usually y is equals to mx plus c. Basically, that's regression. So even when you're defining regression, like the normal definition of regression is usually like, it's usually a statistical, or even it can even be used in psychology terms to show change over time, regression. So it uses, so now the linear regression algorithm uses regression analysis of mathematical statistics to determine the quantitative relationship between two or more variables. So it is a type of supervised learning. This is a simple linear regression. So it takes me back to, you remember when we said we have features and we have now the output, which we usually call label. Features are different combination that will give us the output. So I gave an example for a house. We can have the number of bedrooms, the number of living rooms, the number of bathrooms, the wall color, the tiles color, etc. Those are features. Then they are going to determine the output, which is now the house price label. So this is just a simple regression where we just have one feature and one label. So we can have as many features as possible. So linear regression, it is tries to draw the baseline of fit. I know we have all done like mathematics where we are trying to draw the baseline of fit in several points, several data points. Yeah, so that's what it does. But now because it's an algorithm, it's a powerful one because it can take as many features as possible and determine the baseline of fit for all those features. Yeah, so I think now the algorithm comes now with the power. Now it's able to do for multi-dimension as many features as possible. Yeah, but that's how it works. So the model function of linear regression is as follows. Remember we talked about the weight of the parameters. So this is an equation. I know I said y is equals to mx plus c, but now this is now the equation for linear regression now. H is equals to W superscript T x plus B. Now where B is the bias term, where x represents the sample and W represents the weight. Again, you don't need to cram these formulas, but you also need to understand how they work, you know. Yeah, you don't cram them. You'll understand them with time. So linear regression assumes that features are related to the label. So it bases its output on that assumption. So it will try to see draw the baseline of fit by drawing also the relationship between the features and the label. Okay, so don't forget we want the predicted value to be what else should I explain for this? This is also another formula, but we measure the error also for linear regression because it's a regression algorithm. We are using the mean squared error, the root mean squared error, etc. So don't get hung in the formulas, but just understand how the linear regression works. But that's like, I think I've summarized it for you guys. Trying to take the baseline of fit, then it assumes that features are related to the label. So any question on linear regression? Or any comments? Are we together?
Yes.
Okay. So this is just a more illustration of linear regression. But now it's like an extension. So because linear regression sometimes is not able to capture, remember, it's just a straight line that's trying to pick the baseline of fit. So it can miss out on several relationships, or it can miss out on some aspects of the features. So an advancement of linear regression is called polynomial. Mathematically, we know polynomials. So polynomial regression is capable of now, instead of drawing now the baseline of fit, it can draw the best curve of fit, which means it can capture more data points which means it can increase the accuracy. So it's like a modification of linear regression, basically. Yeah, so when linear regression is not working well, but you know this problem can be solved by linear regression, you can try the polynomial regression. It will improve the linear regression. Yeah. So to prevent overfitting, so remember we said we don't want our model to overfit, we don't want our model to underfit, but most of the problems are usually in overfitting. So because when you overtrain the model, we said it's going to cram the data. So we call, to prevent overfitting in linear regression, we use methods that are called regularization. So we have the ridge regression and the lasso regression. So these are just several methods. I think we encountered ridge and lasso when we were learning about hyperparameters. Yeah, so when you're using these methods, it's like you're training your model, but then at the same time you don't want it to overfit. So you use these methods when you are training, depending on the situation. So sometimes you can find they're called L1 and L2, but then it's the same. L1 is lasso, L2 is ridge. So one does this, it will choose the most important features and ignore the rest. The other one, it's going, okay, so when you're choosing the most important features, it means some features won't be considered in the training. So that's one way to look at it. Then I think that's the lasso regression. Yeah. Then the ridge regression, what does it do? I want to a simple explanation of how it does. But I think a simple example is like it's going to compress the features, something like that. It's going to compress them, and then in doing so, somehow it's going to prevent overfitting. Yeah, so it depends. So some may argue that lasso regression is used for feature selection. You remember we talked about feature selection when we said some features are not really contributing to the output, so we can still ignore them. So lasso regression is also kind of used for feature selection, because if it's going to ignore some features, it's actually selecting the features. Any question? Are we together? And also when, okay, any question? I think I've had an mic unmute.
Oh, I haven't understood. Can you please repeat it?
Okay, so should I start from the linear regression part?
Yes.
Okay. Have you understood the concept of algorithms?
Yeah, I've understood.
So what is an algorithm?
An algorithm. It's the I don't know how to explain it in terms.
You can
Um,
just explain it in layman's language, how you've understood it, no problem.
it's like the kind of the state of the rules, like the way in a recipe, like
Mm,
there's some steps you have to follow.
mhm.
Yeah.
Yeah, so that's like an algorithm. So a machine learning algorithm, I said they usually come from mathematics. Researchers have come out with ways in which they can manipulate maybe calculus or statistics or linear algebra to perform tasks. But now we need now to make this algorithm in a way that a computer can use them. So machine learning algorithms mostly, okay, not even mostly, they are trained to learn from data. That's the point of a machine learning algorithm. It's learning from the data. So these machine learning algorithms have various ways in which they learn from the data. Are we together up to there?
Yes.
So you remember when we said we have several tasks where which we want our machine to do for us. So we classify them into three. We said we have classification task, we have a regression task, then we have clustering task. So we said a regression task. I think I'll just use the same example that I've been using. You are selling houses in you say you are a real estate agent. Then you just want, when people, when we call our house agents, we are always telling them, me, I want a two-bedroom that has this and this and this. So you don't want always to have to go and ask for prices. You want a model that can predict those prices given the features. So when somebody just calls you and tells you, I want two-bedroom that has a kitchen that looks like this, the tiles looks like this, I want the wall like this, you can just feed that information to your model. Then it's going to give you the price. Then you're going to tell your client, this is the price for that house. Up to there, are we together?
Yes.
So now where we're at, we are trying to see how now various algorithm do that, make that decision. So they use various methods. So each algorithm has its own way of learning from the data and giving you the output that you want. So we started with the linear regression. We said linear regression, I gave an example of the line of best fit. And then it assumes that these features are related to the label. So it's going to assume my number of bedroom and my number of this and this, they are all affecting the house price. It's not a bad assumption, actually. When I say an assumption, it's like how it operates. So it's going to create a line of best fit in the features, which means it's like how do I explain a line of best fit? From the features, it's going to what is the ben? I think the line of best fit is usually like the best line from all these properties, which is the most optimal, which is the most optimal property, property of that, of the features. But then now we said, now for a model, sorry, for an algorithm, we're not always going to give it, it's not going to be aligned, because we are not using one feature. Remember, we are checking the number of bedroom, the number of sitting rooms, the number of kitchen, etc. Those will be a lot of features. So an algorithm is able to pick all those features, create a relationship to the output, to the price, and now come up with all those. Now when it's going to learn from the data, that's like the method it uses. I don't know if you're together. Up to there, are we together?
Yeah. Yeah. I'm understanding.
Okay, so far you're understanding. So like the method that it uses. So from our learning data, from our training data, it has learned that it is going to put the baseline of fit in the features. Now when I come and give it my own properties, it's able to give me an output because it has put a line of fit. But now when I say align, it looks like a line, but it's not really a line. We have a lot of features. We can even have like hundreds of features. So the algorithm, it's for somehow going to create the baseline of fit for those features. It's not a line anymore, but that's how it operates. So I said, because now linear regression is based on the baseline of fit, for us to improve linear regression, we have let's say an modification that is called polynomial regression. Now, polynomial regression, from the word polynomial, it's able to plot curves. So instead of taking all these features and creating a line of best fit, it's able to curve through the features. I know I'm using a layman's term to explain these things, but then it can take several curves, which means it can learn from it's more flexible, which means it's better when linear regression is not working well, and that problem can be solved by linear regression. You can just use a polynomial regression. But then um, I think I just scroll up to a certain slide here. We talked about I think I need to pick the slide. There's a slide where we talked about overfitting and underfitting, and then we said when we are training our model, we don't want it to overfit, because when it overfits, it's going to cram the data. So when it crams the data, I don't seem to trace the slide. When it crams the data, when you give it new data, when now it has crammed the data, it has crammed all the data that I have on my estate. So when I come and give it new data that it has never seen, maybe I want my, okay, I think of it this way. In your brain, you're able to analyze for situations. You're able to analyze situations, like you're able to make estimations. So that's what we are trying to do with our model. We are trying to make computer make estimations from our data. But now when it crams all the data, when you give it a different case scenario, it's not able to give you an output, because that scenario is not in the data. So it's called overfitting. So overfitting is where you are training the model because it has learned the data so much. So when you are testing it, it's going to test very well. But now we are deploying it to the real world. Also, another point, the aim of this thing is we want to automate our processes. I want to be able to even maybe create an app. Like me as a real estate agent, I can create an app where people can just go and input the properties of the house that they want, and then they can see the value, the price of the house, without even having to go to the site, without even them having to call me. It's actually reducing my work as a real estate agent. So instead of now receiving the phone calls, somebody will just go search this and this from my app. This is the house that I want. This is the price. Can I afford it? What about this and this? Then they can just call me and tell me, hey, I want a one bedroom that is located in this place, that is in an apartment, etc. Because I've already cut all that work of having to tell people this and this. So I want my model to be able to do that. But now my client is coming with different requests. So I want my model to be able to take in those requests and estimate the prices very well. So I think that's like the bigger picture of AI and everything. How we are making our work easier using AI. So now linear regression, it's trying to put the line of the best fit. Now I don't want my model to overfit. And that's where these two come in. These are like, look at them as methods in which I will use for linear regression to make sure that my model will not overfit. So up to there, are we together? Hello, are we together?
Yes, we are together. I'm together.
So have you understood, like, let's say the concept and even linear regression?
Yes, I've understood.
Okay, so yeah, so these are just the various ways in which this algorithm do the task. So yeah, that's for linear regression. We have another algorithm that's called logistic. This is for classification. As I said, don't cram the math, but also at least have an idea. But then don't bother so much. There's nowhere you're going to put this formula, because most of them have already been put into programs, been put into libraries, and so on. But it's good to know how is it working. So it's a classification algorithm. Basically, it's used for classification. How do I put it like this? I'm just going to use this. So as a logistic regression algorithm, we can say, let's say from below 0, they fall to category 1, and above 0, they fall to category 2. So when we run this algorithm in through our data, it's going to categorize based on what it's going to learn from the features. Don't forget that machine learning algorithms, they are designed to learn from the data, to train from the data. So according to our training, it's going to categorize some output to this category and others to these categories, and that's how maybe it functions. I think I've summarized it as simply as I can, and I think this one will help us understand. So they are both linears to some extent, but now logistic regression uses a function that's called sigmoid function. So it's mostly used for binary classification, but with time we are going to see how we can make a classifier classify more than two classes. What else can I don't want to over explain the formulas also, but basically that's what it's going to do. When we run the algorithm through the data, it's going to categorize the data. Then now the output will be in categories depending on where it has fallen in this sigmoid function. I think that's like the simplest way to put it. So any question? Okay, now if you want logistic regression, or if you want any classification algorithm to classify more than one classes, we apply function that is usually called a softmax function. So this softmax function is like it gives different ranges in which you can classify, and that's how we are able to apply classification algorithm to various classes. Even for neural networks, you use a softmax function in the last layer before the output, and that's how it's going to classify more than two classes. Any question on logistic regression, or even on regression, or on the class today? Okay, and also I encourage you guys, maybe the terms might feel new to you, but when you come back again, it'll just be like, wow, okay. So you'll find out yourself understanding better. So we have another algorithm that's called decision tree. I think decision tree basically is not like a new term, it's a decision tree. So it starts by splitting the first decision, then it is split, it creates a whole tree. And then now the output is now the maybe the best case scenario output. So it uses like the decision tree method to make decisions. I think that's like the most basic explanation of a decision tree. So if you want it to classify, it's going to start the first classification. Is this house a mansion or a bungalow? Classify bungalows, houses. Then it's going to create more trees until it comes to a solution. So yeah, that's called a decision tree. But now we have, okay, this is the structure of a decision tree. We have the root node, subnode, then the end game is the leaf node. Depending on, it's a classification algorithm, but it can also be a regression algorithm depending on the circumstance. These are just like more explanation of how it works, the formulas behind uh the classification, the tree classification, and so forth. So I won't get into details a lot, but then if you have a question, you can still ask, no problem. Yeah. So basically, this is how a decision tree. These are several things that you can do to a decision tree. uh there's like a feature selection part. You can also select the depth of the tree. Those are like the hyperparameter for decision tree. There's some attribute that's called pruning of the tree, depending. So when you're using decision tree, there are some things that you can do to make it give you a better output. So remember, we are the ones setting the hyperparameters here. So those are some aspects of hyperparameters. This is an example of a decision tree. I think an example will help us understand better. So we want to see, you're working in a bank and you want to see how many people are going to default a loan. You're given a loan to people, then you want to see characteristics of somebody who's not going to pay the loan. So maybe you have several features. This is the data that you are using to train so that you can use it in future before you give somebody a loan. I know it's bad, but yeah, it's true. Before you give somebody a loan, you're going to determine this person is single, this is their income, are they going to pay me back? No, I'm not going to give like a loan category or something. So it's going to start. This is the features that you've given it. So did this person refund? Yes or no? What is their marital status? Single or divorced? So if you can see, it's like it's splitting the data, but in form of a decision tree, in form of a decision tree. So that's how it works basically. So it's good to know how it works, but also work with it. So I think I'm usually for trying out to see if I use a decision tree, how is it going to work with my data? Yeah, so yeah, basically that's it. Support vector machines. These ones are actually, it's a great one. It's very flexible. So support vector machine, it's just a name of an algorithm. So don't confuse the name with machine learning. It's just the name of algorithm. I don't know why they decided to call it a support vector machine. They can be classifiers, they can be regressors. But now let's say we are using it for classification. So their basic model is a linear classifier that maximizes the width of the gap between two categories of a feature space. So support vector machine have a kernel trick. This is an important aspect of support vector machine, which makes it an nonlinear classifier. So the learning algorithm of support vector machine is optimal algorithm for, okay, so what is it going to do? Let me use it for binary classification. We have two classes. So it's going to separate the two classes, but then create as big gap as possible between the classes. So which means when you're giving it a new category, it's either it falls to class A or class B, because now the classes are so much separated. So I think that's how it works. But then it has like special characteristics where it can go, it's multidimensional. It can do that for as many classes as possible. Yeah, it's usually a powerful algorithm, by the way. So I don't know, so far, any question? Or any comment before I continue? Are we together? Are we understanding? Guys, are we together or are you exhausted? Somebody say something. I don't want to be speaking alone. So any question? Mhm.
We are together.
Okay. So we have an example of a support vector machine. So you see, this is linear regression. It's trying to find the line of best fit. But now for support vector, it's going to maximize the distance. It's going to say this range, this whole range. This is now where the class separate. So it's like giving it a range instead of just one line to separate the classes. Yeah, this is just like the logic behind the algorithms, guys. But now, because of the kernel trick, it is able to deal with nonlinear data. So when you feed it to this data, it's going to separate it very well. The red from the blue because it's able to cut through various dimensions. And I also hope I'm not using complicated terms. Yeah, so using the kernel trick, it's able to, cut through various dimensions and create this type of output. So yeah, I usually say it's a powerful algorithm. Another algorithm is called k-nearest neighbors. This is a classifier. It's usually creates a relationship between neighbors. Okay, so it's a theoretically mature method and one of the simplest machine learning algorithm. So the k-nearest samples. So it's going to say it's like grouping the classes based on the closeness. How are they close to each other? I think this next slide is going to explain k-nearest very well. I want a slide that explains it simply. Just return to the first one. So k-nearest neighbors, let's say the k actually is actually a hyperparameter. So let's say you want 3 classes, k classes. K the number of classes that you want. So you take this data, give me 3 classes from it. So it's going to inspect the data and put 3 classes based on how close the data points are, on how close the features are related. I think that's the best explanation. Yeah, so it uses that the k is a hyperparameter, but also because it's a hyperparameter, which means when you're training, it can overfit, it can learn too much from the data or underfit depending. But also a larger value of k indicates higher probability of underfitting. A small value of k indicates a higher probability of overfitting. So it's a hyperparameter, so you can set it. I have another algorithm that's called naive Bayes. I usually call it naive Bayes. It's also a classifier. It uses probability. And it's called naive because you remember when we said for linear regression, linear regression assumes that features are related to the output, the label. Now, naive Bayes, it's naive. It just assumes these features are not are independent. They are independent. So just to go back on, linear regression assumes that features are so related, and then they are related to the model, not to the output, to the label. But now naive Bayes assumes that every feature is independent. Every feature has independent contribution to the output. But somehow it gets the work done. Okay, that's why it's called naive Bayes. So, for example, for this, if a fruit is red, round, and about 10 centimeter in diameter, it can be considered an apple. So, but naive Bayes believe that each of these features are independently contribute to the probability. So, a linear regression would assume red is connected to being round and being 10 centimeters. But now for naive, it will assume red is independent, being round is independent, 10 centimeter is independent. Then now, just using its own method is going to determine, it's going to predict well. I think that's like the simplest explanation I can give. So I know the algorithms are many, but over time you're going to realize they're not as many as you think. Yeah, then each has its own strong points and weak points. So ensemble learning. So you remember when we were doing our decision trees, then we said that we have gradient boosted decision tree and then we have random forest. They are all like variants of decision tree. So we call ensemble learning because they combined learning. So you can combine several decision trees to form a random forest. And also you can use another method that's called gradient boosted decision tree also to, it's like an improvement of a decision tree. So ensemble learning is that combination, combining various decision trees to come up with an output. So they use different methods. Some do the average of the output. Each decision tree has its own output, so the average is the overall output. Some will pick the I think the best, like the best output, depending on the method. So all these are variations of decision tree. So you can find XGBoost. It's just an algorithm that's a variant of decision tree. Yeah. Random forest. I think we've said that. This is also just a continuation on ensemble learning. And unsupervised learning, K-means clustering is usually like the most common one. So it's also the same. You just give it random data. Don't forget that unsupervised learning, we don't expect an output. We want the algorithm to learn from the data and give us the pattern. So you can say categorize this data into this number of classes, into these K classes. So it's going to find a pattern in the data and give you. So don't confuse KMN with K-means clustering. There are different algorithms. Another for unsupervised is called hierarchical, from the word hierarchy. So it's like classifying based on hierarchy. It's like top down. This is like some sort of a tree, but also in unsupervised learning manner. I think that's a better explanation. I think that's all. I think we have covered basically everything in algorithm. So we have defined, at the end of the course, we have defined different types of machine learning, the problems that machine learning's algorithms solve: classification, regression, clustering. We have learned about data preparation, data cleaning, the whole life cycle up to model deployment. We have learned about several algorithms. We have learned about hyperparameters. We have learned about optimization methods such as the gradient descent, and so on and so forth. So any question? Any comment? Just say something. Even if you've not understood anything, just say something. So any comment or any question? Audrey. Tamia, any question? Any comments? Have you guys understood our today's session? I want feedback. Like, have you understood today's session? Is it complicated or is it just average? I just want feedback from you guys.